So in this video I'm going to talk about scale up and basis. So here's an example of a process. It just looks like it's a mixing process where we have two different feeds coming in, CH6 benzene, and then we have C7H8 coming in, 1 kilogram of each, and they come out and they mix and they come out here and we form this final mixed stream, which has a total mass of 2 kilograms, a mass fraction of 0.5 kilograms of C6H6 per kilogram, and then also a mass fraction of the C7H8 of 0.5. So this is just process right here. Now we can simply go ahead and multiply all of the numbers in this problem by 300. And what we've done is we've essentially scaled up the problem by a factor of 300. If we do that, you'll notice that this is 300 kilograms, 300, 600. The mass fractions, however, stay the same. They're still 0.5. Half of this flow stream, half of this stream is still C6H6, and then the other half is C7H8. This process is essentially scaling up or scaling down. We can take any process and multiply it by a constant value, and all of the flow rates will change, or the flow values will change, but it doesn't change the overall problem. The mass and mole fractions, however, will stay the same. And this is the concept of scale up. So if I have a process that I've gone into the laboratory, for instance, and I've made this little mini mixer in the laboratory and it pumps in, a kilogram, that's fine, a kilogram here. But then I can go ahead and build a bigger mixer. Say I go into a chemical plant and I build this tall giant mixer. As long as I'm having, the same ratios and everything else, everything comes out the same except the flow rates are multiplied by the scale up factor, but the mass and mole fractions are the same. So this is useful when you're dealing with a process and you want to double it or cut it in half. It's kind of like baking or cooking. You could easily double a recipe or cut a recipe in half, and that what you've essentially done is scaled it up. So just a reminder, flow rates change, but the mass and mole fractions don't. We could also, here's the bottom example of a scale up. It's a little trickier, but what's happened here is that we've converted from kilograms to pound moles per hour. So we would just simply take the same numbers here, but we've just converted the units. So we would have to use a conversion factor, go from kilograms to pounds mass, like here, and so you could look those up. We've also assumed that it's a flow rate per hour, but you'll notice that the underlying flow rates don't change. It's still 300, 300, 600, so it's still, these two add up to here. The mass fractions did not change. Instead, the mass fractions here are just expressed as 0.5 pounds mass of C6H6 per pound, total pound mass, and then the other one for C7H8 is 0.5. So we can also change units. Now, tricky part here is if we wanted to change this to moles, we wouldn't multiply it by a common scale-up factor because we would have to use the molecular weight. So 1 kilogram of C6H8 is a different number of moles of 1 kilogram per C7H8. So we have 1 kilogram of C6H6 has a different number of moles as C7H8. 1 kilogram of C7H8. So we'd have to use the molecular weight, and I'm confident you can do that by taking a kilogram of this and converting it to the number of moles using the molecular weight, but that's how we would do it. One other concept I want to talk about is the basis. So the basis is just simply a known value on a given stream. So let me just example here. Let's just assume I have a flow. We'll just do another mixer here. So we have something mixing, and I know the mass let's say we'll know the mole fractions. I'll just say here this is A and B, and we'll just say 1 mole per hour flowing, and we'll call this X moles per hour, and I'm going to say this has a mass fraction of 0.5, did I say mass? I meant moles A per mole. And so by the addition of the relationship between the mole fractions at 0.5 mole B per mole. And let's just assume that I know some information here, well, about this coming out. I'll just label this as Y moles per hour. Maybe not the best variables, but they're still variables I can choose. And let's just say it's 0.4 mole A per mole, 0.6 mole B per mole, and we'll just say this is 0.3 moles A per mole and 0.7 moles B per mole. So this is just a problem I just made up off the top of my head. In this case, the known flow rate is right here in this stream, and this is the basis. This is the number which we're going to use to solve for this problem. So once we know this molar flow rate here, we'd set up our material balance equations and we could try to go about solving it and so forth. But this is the basis. It's our known flow rate. We could change this. So if I go ahead and change this, what if I, let's just say the basis is now 2 moles per hour. Well, that way we know just from talking about scale up, that would just simply double these values, x and y, compared to the solution if it was 1 mole per hour. So if I just simply doubled the basis, that would double these values here, and so forth. So that's the basis. Now sometimes we get problems where we don't have any known flow rates. So in this case, it may not be given that information, and let's just call this F moles per hour. So we may have some unknown flow rates. So we know the mole fractions, but we don't know the flow rates. And in this case, we can assume a basis. So I don't know anything about the flow rates, but I will assume a basis. And then what I'll do is I'll just assume F is equal to 100 moles per hour. Just a round, nice round number. And so once I've done that, I've assumed a basis of F, what it is, then I can go ahead and solve for X and Y here based off this assumption. And then if I need to, I can scale everything back down to an appropriate value, whether that's 1 mole per hour or whatever. And that's the idea behind basis. Sometimes you're not given information about flow rates. You may be only given information about compositions, and what you'll have to do is assume a composition for one of the flow rates, and that assumed composition, or you assumed a flow rate for one of the streams, and that assumed flow rate for that stream is the basis.